Uh, Hello everyone. So today I'm going to talk about my project during the postdoc, which is about repurposing a catalytic cycle as power source. So what we are interested is molecular machines that operated progressively in the presence of energy source, which is called autonomous molecular machines. The left one is kinesin, so it's a biological molecular machines which continue to walk along the track inside the cells and transport cargo inside cells. And it continues to operate as long as the energy source, in this case ATP, is present. The middle one is a light-driven molecular motor. It's a synthetic example. And the right one is a chemically driven autonomous rotary motor. Again, this is a synthetic example. And the key requirement for designing these kind of autonomous molecular machines is to supply energy, because without supplying the energy, you cannot maintain directional motion. So the first thing to consider when we design these autonomous molecular machines is how to supply energy. But before going into my project, I want to clarify the difference between non-autonomous and autonomous molecular machines. So this is an example of a non-autonomous molecular motor. It's made of two interlocked macrocycles like this. And what this system does is to rotate one macrocycle on the other macrocycle in a directional way. So how it's done by the stepwise operation. So you first, can you see this group? So this TR is the blocking group, which blocks the movement of a macrocycle. And the first step is to remove this blocking group, and then this blue macrocycle can move from the top binding site to the bottom binding site. And then we change the structure of the bottom binding site and attach the blocking group again and remove the other blocking group at left, so that the macrocycle can travel back from the bottom binding site to the top binding site. And then you can achieve directional motion. But you can see it's very tedious. In contrary, operating autonomous molecular motors is much simpler. So as long as the energy source is present, you don't need to change the operating environment. This is, again, a molecular machine made of two interlocked macrocycles. And as long as the chemical fuel is present, this magenta macrocycle travels along the black track in a directional manner. And what we are interested is this type of autonomous molecular motor, because it's simpler to operate and it's closer to what biological systems does. So going back to our main question, how to supply energy, the key component for supplying chemical energy to the system is chemical reaction cycles. So this is an example of autonomous molecular pump that we developed during my PhD. So what this system does is to pump up this blue macrocycle on the catchment track by this fuel attachment reaction and the waste removal process. So these two processes make up a full reaction cycle, and the conversion of fuel to waste supplies the energy to the system. However, it's often difficult to find compatible reactions that make up a full cycle, because they need to operate under the same reaction environment. And even if you can find good combinations, they often suffer from problems like background fuel decomposition. For example, in the case of this pump system, as much as 90% of the fuel gets decomposed without even reacting with the pump, so it's a very inefficient system. Various reaction cycles have been developed, but many of them suffer this problem. So what we did was to realize a simple and general approach for developing a chemical reaction cycle, and that is to repurpose a known catalytic reaction. So this is a common approach, which is to combine different steps to make up a full cycle, while our approach is to repurpose a known catalytic cycle. When you compare the general scheme of chemical reaction cycle, this left one, and a general scheme of a catalytic reaction cycle, which is this right one. You can see they are exactly the same. So it means we can repurpose a catalytic reaction cycle for supplying energy to the system. The advantage of this approach is that we don't need to worry about the compatibility of multiple processes because all of the processes in a catalytic cycle are already known to act under the same environment. And also, we can suppress the background through decomposition because the substrate to product conversion without the catalyst is usually much slower than this conversion through the catalytic cycle. More specifically, the aim in our project was to achieve transient self-assembly. So it's not really molecular machines, but the same approach can be applied to molecular machines too. So here, this is the overall chemical reaction network of the system. And this blue molecule is the fuel, and these two black molecules are the wastes. And what we want to achieve is to control the assembly state of molecule in a transient way. So you start from this red molecule, which is a low assembling state, and after the addition of the fuel, it's converted into this orange state, which is much more prone to self-assemble. And after the consumption of the fuel, it returns to the original state. So to achieve this, we tried this simple mixing experiment and indeed observe transient formation of white assembly species. And we also confirmed that this red molecule acts as a catalyst for the fuel to waste conversion. This is an observation by a microscope. You can see after the addition of the fuel, the spherical aster-like structures were formed. So it's not amorphous random assembly. They have well-defined structures. And these assembled structures continue to exist up until 60 minutes and then gradually disappeared. So it's a transient behavior. So the main message of my presentation is very simple. We can repurpose a catalytic cycle as a power source of the system. And this is a simple and general approach for developing chemically driven systems. So it can also be applied to autonomous molecular machines too. With that, I'd like to thank the people in the Herman's lab, and thank you for the organizer for the invitation, and thank you for your attention.
Is there a concept for catalytically driven chemical power sources that you can turn on or off with an external signal? Like it only works when you don't shine light on it or something?
Yeah, I think that's possible. So this system is about autonomous system, but you can add some, for example, molecular switch, light-driven switch, and tune the function of this motor. That's, I think, possible. I think it's not been done yet, but yeah, that would be interesting.
What is the rate of background fuel consumption for your system, and how does it compare to other fueling sources?
Background fuel decomposition?
Yeah, hydrolysis of the kind of reagent.
Yeah.
Is there much background
in this
rate?
system. So you mean in this system?
Yes.
Okay. It depends on the pH. At low pH, you can see the ratio between the background fuel decomposition, which is shown by this gray bar graph,
Okay.
and the fuel consumption rate in the presence of the this molecule 1 is like 1 to 6.3. So only 10 or 15% is decomposed in the background. But if you increase the pH, this ratio gets decreased, and at pH 7.9, there was no statistically significant difference between these two. So it's not really suppressing the background decomposition.
Okay, thank you.
Thank you so much, Shuntaro. Fantastic.